Hello all. Thank you for joining us today. Today we're going to be talking about how to say no, or in other words, how to negate mathematical statements. So I've got a statement right here. If P, then there exists an X in D such that Q of X and R of X. We'd like to figure out how to find the negation of this. So say, for example, maybe P right here means Wabash is a good school, and we're going to say that this here, maybe D, is people, and then so this X would represent a person. We've got Q of X maybe is X went to Wabash, and then R of X means X is famous, and so then this whole statement might translate to something like, if Wabash is a good school, then there is somebody who went to Wabash and is famous. Maybe, though, you disagree with all of this, and so you want to figure out how to say no, that this statement is not true. So it's easy enough to stick our not symbol out in front of any statement. If we do that, we'll get a statement that has the opposite truth value as whatever is here inside the parentheses. So that is exactly what a negation of a statement is. Something that has the opposite truth value of the original statement. Whenever the original statement is true, negation is false. Whenever the original statement is false, negation is true. But we want to actually see if we can parse that a little bit. In our English translation here, all we'd be able to say right now is that it's not the case that if Wabash is a good school, then there is a famous person who went to Wabash. We'd like to figure out a little bit better what that actually means, so we're going to look at the negation. And again, the nice thing about math is that we can ignore all of this individual meaning and then just focus on the expressions, figure out how mathematically to negate them, and then we'll be able to go back and see if we can reinterpret that based on the context that we decided on. So, before we get started, let's review a little bit of what negations actually do. This is sort of piecemeal knowledge, but let's zoom in a little bit here and say, okay, if we've got a statement that looks like not P, for example, a double negative, those cancel out. That gets us just to our original statement. If we have something that looks like not P and Q based on De Morgan's laws, that's going to become not P or not Q. In some ways, negations tend to flip everything that we've got originally. So likewise, if we've got not P or Q, that turns into not P and not Q. For quantifiers, so if we have something that looks like for all X in D, P of X, the comma there is optional. If we want to negate that, that's going to look like opposite of for all would be there exists. X still gets to be in the same domain that we're considering, but we would put a negation here in front of the P of X, and then, so this is sort of saying, if we're going to say that it's not the case that for every X in D, P of X is true, then there would be at least one X that makes P of X not true. Similarly, if we're trying to negate something that looks like, there exists an X in D such that P of X, so if we're saying it's not true that there is an X that satisfies this property, that's the same as saying that same as saying that every X in our domain doesn't satisfy the property, so for all X in D, not P of X. Okay, so that takes care of most of our standard symbols and how to negate them. We do want to take a look at how to negate something that looks like if P then Q. That one is a little bit unusual. There's not really a good way to flip an if P then Q. But remember, originally we have that something that looks like if P then Q. That's logically equivalent to not P or Q. This thing is true if P is false, just it's not applicable. And it's also then true if P happens to be true, and Q is also true. So then, I guess, yes, if P is true, then not P would be false, but Q needs to be true. So that works out. And so if we want to negate if P, then Q, that's the same thing as negating not P or Q. And so then we can say, okay, the negation of this thing, we can pull in that not symbol there. We've got our not P, so that's going to be P. The or becomes an and then the Q gets the not symbol applied to it. So the negation of if P then Q is P and not Q. P happened, but Q didn't happen. So that would be, in general, the rules that we're going to use. We're going to want to now take a look at how to negate this statement right here, making use of those rules. So, first thing, I'm going to look at my outermost layer of my statement. Right here, I'm seeing on its big complicated statement, but on its outermost layer, I've got this P there, and then this whole big statement here. So I'm starting out by negating one of these if P then Q type statements. I can do that easily enough by using our translation right here. So this is going to be logically equivalent to something like, it'll be P, so P right there, and not all of this. So if we think of the meanings that I was thinking of just to help us parse this statement, we're saying Wabash is a good school, and there doesn't exist somebody who is famous and went to Wabash, which makes a little bit more sense when we say it in English, but we'd like to keep on going, see how far we can work that negation symbol inwards, just so that we can get a better understanding of the statement. So P, we can leave that alone now. We've got this negation here. We'd like to pull it in. As we said, our next layer is exists an x in D such that all of this happens. So we've already looked at how to negate that. The exists flips, we get n for all. So for all x in D, this whole thing is going to become, I guess we're going to stick the negation in front of there. For all x in D, not all of this. So this is going to say, so this would say Wabash is a good school, and everyone who went to, I guess, and everybody, for all people, it's not the case that they went to Wabash and are famous, which is still kind of linguistically awkward, clearly. So let's see if we can get that distributed in a little bit more. P and for all x in D, by De Morgan's laws, that would become not Q of x or not R of x. And that's about as far as we can go with the setup that we've got. Using our meanings, we're saying Wabash is a good school, and for all people, either they are not famous or they didn't go to Wabash. So I don't know if that's actually better, and I also don't know for sure if that's actually true either. We've got our slight difficulty with real-life examples where things don't quite line up into neat truth values like they do in mathematical statements, but at the very least, we have negated the statement, so we are done with this example. So for your own practice, try out this same process. Find the logical negation of the statement there exists x such that P of x, or if Q, then R. Don't worry about meanings or anything, just see what you can do applying the negation to all of this. Okay. We sort of talked a little bit about meanings and negations. I would like to take a bit more of a look at that process using meanings, using negations of logical symbols to get meaning out of a negation of a statement. So I'm going to start with a statement here. Every prime number is odd. You can get certain mathematicians to go down rabbit holes about this, but we've just got a statement. We're going to try to translate it. So first, I'm going to translate this into logical notation. So I'm going to say we've got this every here. We're talking about numbers. Maybe I'm going to say D, my domain, is, and really when we're talking about prime numbers, we're talking about integers or maybe even natural numbers, whole numbers. So I'm going to say that my domain is the natural numbers. I'm going to say P of x means x is prime, so that I can talk about being a prime number, and then Q of x means odd. So now looking at this, it's not really clearly in any of our logical formats, but we've got this everything here, so I'm going to take a look at that. Every, even though it's starting with an E right now, is the same thing as saying for all, so you've got for all numbers. I mean, I could even just use that natural number symbol there. That would communicate what I'm talking about. You're saying every prime number is odd, so we're sort of saying that if a number is prime, then it is odd. So this is sort of a hidden if-then statement. I'm going to say if P of X, then Q of X. So next, I want to negate this. So I'll stick a not in front of everything that I just wrote down. We're going to say it's not the case that for all x in D, P of X, if P of X, then Q of X, but we do want to figure out what that means. So I can now ignore where this came from, just focus on the math. Let's see. Our outermost layer here is our for all x in D part, and so I'll negate that. There exists an x in D such that not if P of X, then Q of X. Then I'm going to work on pulling that negation in there. Recopy. There is an x in D such that, and again, negation of if P then Q was P of X and not Q of X, so and not Q of X. We've pulled that negation symbol in as far about as we can. It's not outside any parentheses, which is usually the textbook's way of kind of assuring that we've got our full negated statement. Now our question is, what does this mean? So if we want to translate this back, we're going to need to go and look back at the meanings that we assigned. So we said that we've got D is the natural number, so there is a number. That's what this part right here means. Is a number. And then here says x is prime, so which and then we've got and not Q of X. Q of X said that X is odd, so and not odd. Or if we want to push this a little bit further, often in math, we can apply negations based on context, and so we know that there is a nice negation of not odd. If a number is not odd, it's even. So we can say there is a number which is prime and even. All this works whether our original statement or its negation is true. In this case, we do have a number that is both prime and even. It happens to be the number 2, but that's kind of beside the point here. So, for another exercise, we've got another mathematical statement. This one happens to not be, I guess, the original statement is true. Its negation won't be. Again, we don't really care. We just want to figure out what the negation is. So, we've got the statement every number larger than six is positive. Just as sort of an insert, larger than 6, we often denote that as x greater than 6, and then positive means x is greater than 0. So every number bigger than 6 is bigger than 0. That sounds pretty true, but we want to go through the process of negating it anyway, so A I'd like you to translate this statement to logical notation. Then B, I'd like you to negate the statement from A, and then C to finish it off. I'd like you to translate your negated statement back to English. Thank you for watching. Enjoy.